Today we will solve another graph problem. Here you are given a bunch of source and destination and what is the fare of flying a flight between those cities. So let's say this is the graph. So here there is a direct flight from 0 to 1 and its cost is 100. Similarly, there is a flight from 0 to 2, its cost is 500, and we have a flight from 1 to 2 and its cost is 100. And it's given as a pair of three numbers: source, destination, cost. Source, destination, cost. So using this you can form this graph. So this fare denotes the distance. If you look in terms of the graph terminology, these cities denote the nodes or vertices, and this existence of flight between two cities denotes the edge, and the price of that flight denotes the distance or the length of that edge. So these are given, and you are given a source. So source is 0 in this case, and you are also given destination. So you know the source, you know the destinations, but you have a condition. You have to take at most k stops. So there may be direct flight, maybe that is the cheapest, but maybe that indirect flight is more cheaper. For example, if you want to go from 0 to 2, direct flight costs 500. A flight which takes a halt at 1 costs 200, 100 plus 100. But there may be that there are more nodes here, and that 4 or 5 hops, and ultimately you reach 2 is even less than 200. But the condition is that number of hops should be at max k. So that is the constraint. So you may straight away think that it's looking like a shortest path problem, like the Dijkstra case. There also we are given a source. We have a notion of directed graphs, and all the edge weights are positive, just like the flight prices are positive. But there we are only calculating the minimum distance. Here we are not calculating the minimum distance. So in Dijkstra, if you remember, we are calculating, updating the distance level gradually. So when we find a better path, we update that. But here that constraint k does not allow us to reach the optimum solution, but you have to stop once you reach k hops. So let's say, let's look at an example. So if you run Dijkstra here and a is the source, so its distance level will be 0 and everything else will be infinity. So what we do, we pick the minimum element, we add the source to a priority queue, and then we pick the minimum element or the top of the priority queue, in this case min priority queue or min heap. So this will be picked, and then you look at its neighbors, and so in order to reach a you need 0 hops, because this is the source, and 0 price also. Then we look at its neighbors. Its neighbors are b and d, both have infinity level. So from a we can reach them using 10 and 5 prices. So we compare whether we got a better price or not. So obviously 5 is less than infinity, so we make it 5, and also hop of 1. Since the hop of the node from which we came was 0, we add 1 to its hop. So we reach d. This is not hop, but this is kind of edge you can say. One edge we took, hop. One hop denotes 2 edges. So from a to b and b to c. So here it will be 1 stop. So k will be 1 in this case. So edges will be 1 more than the hop. So here this denotes the number of edges. We took 1. Here also we got a path of length 10 from source, which is less than infinity. So we update it, and again 1 edge is counted. Next, this is popped from the queue, and b and d are pushed into the queue. So b is pushed with a distance of 10 and a hop of 1. And then d is pushed into the queue with a distance of 5 and edge of 1. This is strictly 1 less than the k due to this region. So these two elements are in the queue now, priority queue. So we will pick the minimum. See, this is the min heap. So which is the minimum? D is the minimum. So pick D out. So let's strike it out. Now we see that we look at the neighbors of D. So the neighbors of D are E. So its minimum distance is 5. So this distance will be finalized. And when we pop, we also compare, have we reached the destination? If we have reached the destination, so when we pop something from this queue, the minimum, that is the final level of that node. So D is finalized. So let me color it. A was finalized when we popped out. Now D is the minimum. So D's distance is final from the source. So when we pop out, we also check whether we have reached the destination. If we have reached the destination and this length is final and this is well within the k, then we return it. So D is not C. So we continue. So we look at neighbors of D. Neighbors of D are E. So 5 plus 2, 7. And hop will be one more, or number of edges, sorry. 2 edges, that means 1 hop. So we insert it into the queue, E, 7 and 2. So here maximum number of edge can be k plus 1 or 2. So next time when we pop out element having a edge of 2, we will not look at its neighbor, because all its neighbors, we will go from this node, will have 3 edges and we can take maximum 2 edges. So we have inserted E into it. Then what is the next neighbor? Next neighbor is C and its distance will be 14. 14 and again 2 edges, this and this. And its next neighbor is B. So although B is already here, but we will keep inserting. So if whichever is the minimum B, that will be picked first. So whatever is the shortest distance within that limit will be figured out. So B, here it's 8. So we update it. If it was more than 10, we would have not pushed it, but we got a path of 8. And it's well within this bound, that is 2 edges. So we put it 8, 2. And there are no more edges, so we stop. Next we pick the minimum from this. Minimum is this 7, that is E. So we look at the neighbors of E. We will compare if it's the destination. It's not destination. Then we see how many edges are there, 2. So we know that I cannot look at its neighbors because that will add additional edge. So we do nothing with E. Next we look what is the, so let me mark it finalized. Next we see which is the minimum, 10, 14, 8. So minimum is B. So we pick B. Again it has, B is not the destination and the number of edges is 2, which is equal to this maximum limit. So we cannot look at its neighbors. Going to its neighbor will add one more edge. So we do nothing with this B. Next minimum is again B, this one. So we pop it out. So B's minimum is 8, but the path that will go to C will not be the shortest path, but will be shortest within this bound. So next we picked this B, 10, 1. So this is less than maximum number of edges, or k plus 1, less than k plus 1. So we look at its neighbors. Its neighbors are C, D, but D is already finalized, although you can add it, but it will never get picked. It will get picked, but it will never get processed since we will put it with a edge of 2. So we can optimize our solution so that we don't insert a vertex again if it's finalized. But let's insert it for now. So let's insert D, and this is 10. 10 plus 2 is 12. and number of edges is 2. And the other neighbor of B is C, which we will insert again. So C will be, this is 10 plus 1 is 11, and number of edges will be 2. So now we are done with B. Now what is the minimum here? 14, 12 and 11. So we will pick 11, C. So let's just strike it out. So we popped C with 11 and 2, and we see whether this is the destination. Yes, this is the destination, and we return, since whenever we find the destination we return. So return 11. So let's see that the minimum shortest path from A to C is of length 11 within this condition. What is the global shortest path? The global shortest path would be this: A to D to B to C. Let's count the distance. A to D is 5, then D to B is 3, then B to C is 1. So 5, 3, 8 plus 1, 9. But here we have taken 2 hops or 3 edges. So this is not valid. What is the next one? You can come to A to D, D to C. This is just 1 hop, but its length is 14. And A to B, B to C is 11. And that will be the minimum under this condition, and which we have correctly returned here. So let's write the code for this in C++ and Python. So let's build the adjacency list first, which will be a vector of vector. So the outer vector will be of length n, where one space will be for each of the n vertices. So let's take an example. Let's say we have a simple graph. Let's make it 0, start from 0 to n minus 1. And this is 100, this is 50, this is 10, this is 20. So how we will represent it? Here n is 4 vertices are there. So we will have a space for all the 4. And what are the adjacent vertices of 0? It's 1 and 2. So we will reserve a space for 1 and 2. If it's unweighted, we don't need to store the weight, but since it's weighted, we will store the neighbor and how far it is from this node 0. So 1 is at a distance of 100, 2 is at a distance of 50. Then what are the neighbors of 1? Only one edge is outgoing, which is towards the 2. So we have 2 and length is 10. From 2 there is only one edge, so it's 3 and 20. And from 3 there is no outgoing edge, so this will remain empty. So this is a vector of vectors. So this is a vector here. So this is a vector of here its size is fixed, 2 length, so either you can keep another vector or a pair. So vector of pair of int and int. So it may look complex, but it's not that complex if you look at it. So this outer vector will be of size n. This will vary depending on how many. So this vector will be of size number of neighbors or outgoing edges from a given vertex, which we pick from this outer vector. And again within that the length is fixed to each. So if it exists, it will have a length of 2. So let's write it in the code. Vector of pair of int and int. This we will call it as adj for adjacency list. And then let's build it. So for vector of int flight. So flights is itself a vector of vector, and each element in this has three components: source, destination, and price. So ADJ F0, this will be the node source. Destination, and F2 will be the price or the distance. So we have built the adjacency list. Now we will keep the priority queue. And each element will be a vector, and container is vector of int. And the comparator, we will use the default greater comparator. So how this greater comparator works is that it will simply compare integers. Integers can be compared, but if it's a vector of integers, then it will compare the first element of those vectors. So let's say a vector has 50 and 4, and the second vector has 10 and 100. Then first vector is larger, since the first component is 50 here and in there it's 10. So it will compare based on that. And here we will keep the first component as the distance level. So it will automatically keep it sorted based on the distance. We don't need to provide a custom comparator. You can also provide a custom comparator if you are not putting the distance in the first component of this element of priority queue. Let's call it queue, and we will push the source into it. So 0 is the distance, that is the first component based on which the comparison will be made. Then src is the source which is given to us, and k plus 1, which will denote number of edges, which we had seen that will be one more than k, or the stops. While queue is not empty, pick the element vertex with the minimum distance, and then remove it from the priority queue. So the first component, top 0 will be the distance level, and second will be the actual vertex level. So let's call it u. And last one will be the k. So here I am using a small k. It should not be confused with the k that is given to us, which is capital K. Or we can also use edges here, E, to denote edge, since this is actually the number of edges. So let's call it E. And if DST, that is destination, which is given to us, is same as the current this node that we popped out, then we return its distance level, that is D. Else, if E is more than 0, that is we can add one more edge to it, one or more edges to it. If it's 0, that means we cannot add any edge, so we cannot look at its neighbors. So if it's more than 0, then we will look at its neighbors, that is pair int all the neighbors v of u. Q dot push. First is the distance level, so it's d plus whatever is the distance of this element plus v dot second. And next is the level of the vertex level of the neighbor, which is the first component. So here we are storing the node and its distance. So second is the distance, first is the node itself, and we will allow one less edge to it. So here it's e minus 1. So when we pop this element out, we have reached here using one more edge. So one less edge we can afford. So we have done e minus 1. And then if it doesn't return in any of these cases, that is, there is no path using k hops from source to destination. In that case, we will return minus 1. Maybe there is a path from source to destination, but it takes more than k hops for all the paths. Then we return minus 1. And let's run it. So it gives runtime error in some vector allocator int. So we are accessing it without. So let's make it of size n. And this also should be equal. And the answer matches. So let's submit. And the solution is accepted in C++. Now we will look at the Python solution. So we will build the adjacency list. So it will consist of key, and key will denote the vertex or the nodes, and it will for each key we will have a value of list which will hold the adjacent nodes. So let's look at all the elements of flights, which is source, destination, and edge, or the price. So we have built the adjacency list. Next, we will use the priority queue. So this is a list, and we will append it to it source. So now source is only in the priority queue. Now we will use the heap functions, which is heap queue dot heap pop, and pass the queue, and no need to call the pop. It does both in one step. D U E. If U is the destination, return D. If it's not, then check if we have more edges left to add. If we can add more edges, then add it. So look for all the neighbors V of U, and then so looks like there is some indentation issue here. Okay, we will discover that. So heap q dot heap push q, then these values, or d plus v dot second is v1 and v dot first is v0 and e minus 1. So there is some indentation issue, that means there was some error here. So it's p, and let's add this. And let's see if it picks the indentation. Yes, it picks. Looks like it's fine. Now it works, so let's submit. And the Python solution is also accepted.